In this video we're going to see how to train different pattern recognition models. We're going to start by dragging the golf dataset, also called the weather dataset, and we're going to train among the different models available in RapidMiner. We're going to go for predictive model decision trees, and we're going to use the standard decision tree. After training the model, we would like to compute some measurement about how many times is the model making the right prediction. In order to do that, we need to apply the model. We're going to apply it over same data that was used for training the model, and then we're going to compute the accuracy. Accuracy is how many times is the model making the right prediction. So if we run this setup, here we have what's called a confusion matrix. In this problem we have 14 instances, 14 golf games. 9 of them were played, 5 were not played. And this matrix here in the rows, it has the ground truth, the reality. These are the 5 golf games which were really not played, and these are the 9 golf games which were really played. And in the rows, instead of the columns, we have the prediction. The fact that I have a 5 here, it means that these 5 golf games were predicted to be not to be played, and the reality is that they were not played. So we made the right prediction. And there are 0 cases where the model predicted that we wouldn't play, and we really played. So there are 0 mistakes here. The same way, there are 0 cases where the model predicted we will play, and in reality we didn't play, and there are 9 cases where the model predicted we will play it and we did really play. In the confusion matrix, we would like ideally to have only values different from 0 in the diagonal, because those are the times we made the right predictions, and values equal to 0 outside the diagonal. This is the decision tree that we had seen in the theoretical part of this course. It's the same decision tree as the one you have in the slides, and you can see that the accuracy is 100%. It makes absolutely no sense that for from just 14 golf games we are capable of training a model which is capable of getting right every single time whether we're going to play or not a golf game. The problem here is that the model, the decision tree, is being tested over the same dataset that was used for training, and that's promoting that the model memorizes the data. I'm going to copy this setup it's the same setup I had before. And then I'm going to split the data. In such a way that 30% of the data is used for training the model and 30% of the data is used for testing the model. So we're going to use different instances for training. 70% of them they're going to be used for training, and for testing, for applying the model, I'm going to use the remaining 30%. Now I'm going to run this process, and the accuracy I got in this case is 50%. There was one case where the model correctly predicted that we will not play the golf game, but there were 2 cases where the prediction of the model was we are not going to play and we really played. These are the 2 mistakes I have here. This is a correct prediction that we will play, and we indeed should have predicted that we will play it. So in this case, accuracy is 50%. When evaluating a model in this way, I really have no clue whether I was lucky when splitting the data in testing and training, and maybe the dataset I have for testing, it was an easy dataset and I got a really good result, or whether I was unlucky. Another option is using cross-fault validation. In cross-fault validation, what we're going to do is train and test multiple times the model. In order to do that, we're going to split the data in different faults. Typically we use 10 faults, and that means that, for example, if we have 100 instances, we're going to use the first 10 instances for testing the model and the remaining 19 for training the model. Then we're going to use instances from 1 to 10 and from 20 to 100 to train the model, and instances from 10 to 20 to test the model. Then we shall use instances from 10 to 20 and from 30 to 100 to train the model, and from 20 to 30 to train the model. And we'll keep going in such a way that we're going to train 10 different models and test 10 different models and have 10 measurements of accuracy. And we shall compute which is the average and the standard deviation in order to get some sense of the spread of the data. I'm going to cut this part of the setup, and I'm going to look for the cross validation operator. Is a nested operator. And when I double click on the cross validation operator, on the right hand side I should put the setup for computing the performance, in this case the accuracy of the model. So I'm going to apply the model over the 10% of the data which was not used for training, and the model is going to be again the decision tree. So 90% of the data is going to be used for training, the remaining 10% is going to be used for testing. Here we have the number of faults. If we change that, we will use different number of faults. For example, if it's 5-fault validation, then we shall use 80% of the data for training, 20% for validating. And if we run this process, we are not going to get just a number for measuring the accuracy, but we're going to get a confidence interval, 30% plus minus 40%. That's telling us that the real accuracy of this model may lie anywhere between 0 and 70%. And that's much more reasonable given the very small number of instances we have for this model. That's probably a better estimation of the accuracy of the model. Let's go back to the original setup, and I'm going to change the data source. I'm going to remove the golf data. I'm going to drag the iris, and we're going to apply the same 3 different schemes for validating the model over the iris dataset. This is a more realistic dataset. This dataset is large enough to actually learn something from it. If we run the model, we see that when using a 10-fold validation, the accuracy we got is more or less 93 plus minus 10%. If we use the scheme where we use 70% of the data for training, 30% for validating, we have an accuracy of 91%. And when testing and training over the same dataset, we got 98.6%. In this case, I'm promoting overtraining of the model. This will be a best estimate of the accuracy, and much nicer than just a single number where I don't really know if I was lucky. It is a confidence interval such as the one we are showing over here. If, for example, for the decision tree, I tell it not to prune at all, when not pruning, I'm promoting overtraining. So I have changed all the 3 decision trees training schemes not to prune at all. And in this case, I still get more or less the same accuracy when using 10-fold validations. I get a slightly higher accuracy for this scheme, but especially for the first scheme I went up to 100%, because by not pruning at all and by allowing the tree to grow leaves as small as it wants, I'm really encouraging the tree to learn, memorize the training data. And given that the testing data is the same, it's making correct predictions. In general, if we use this scheme for testing the accuracy of the model, if we test the accuracy over the same training dataset, we are overestimating the performance of the model. With this scheme, it's a better measurement than the previous one. What we are not really sure if we were really unlucky or really lucky with the single measurement we got. With the cross-validation, we have a much better picture of the real performance of the model. Given that the last scheme is the preferable one, I'm going to remove the first two schemes, which I have used them just for didactic purposes, but it's much better that you always use fault validation in order to test the accuracy of the models. And I'm going to use some other models over the dataset. So we're going to go inside the cross-fault validation operator. I'm going to remove the tree, and for example, I'm going to look for a rule-based model which got an accuracy of more or less the same as the decision tree. Again, here, for example, this 4 means that there were 4 flowers which were really Iris bicolor and the model predicted Iris Virginia, and there were 7 flowers which were really Iris Virginia and the model predicted Iris bicolor, and these are the 11 mistakes made in this case. Another of the models we have covered in the course is naive Bayes. I'm going to output also the model besides the confusion matrix. Regarding the performance, I'm getting a little bit better performance than the decision tree, 95 plus minus 4%, so it's a little higher and a little narrower, the confidence interval. And regarding the model, here I can see the 3 one-dimensional probability distributions that were learned for each of the 3 features. This is the attribute A1. I can see a lot of overlap among the features. This is the attribute A3, and these 3 Gaussians are the one representing Iris setosa, Iris Virginia, and Iris bicolor. And for example, for A3, which we know is an attribute where there is much more separation among classes, I can see that there is pretty much no overlaps between the Gaussian of Iris setosa and the other 2 Gaussians, and the other have a smaller overlaps. If I go here to distribution table, I can see the mean and the standard deviation for each attribute for each of the 3 Gaussians of for each of the 3 classes. If instead feed into this model the Iris dataset, I feed the Golf dataset, which has some nominal attributes. If I run the process, when checking the charts, if the attribute is numeric, such as temperature, I'm going to again see both Gaussians, the one where we played the game, the one where we didn't. And in the case of discrete features, I'm going to see discrete probability tables represented by bars in this case. These are the same tables and the same type of information that we cover in the practical session of the course. We're going to go back to the Iris dataset because it's a little bit more realistic dataset, and we're going to use a different model. In this case, it's going to be a Bayesian network. For using Bayesian networks, you're going to have to go to the marketplace and look for the Weka plugin. The Weka plugin makes available all the algorithms available in the open source tool Weka within RapidMiner. In my case, I already have installed. You should install it in your computer before doing the next part of this video. If you have installed it, if you have installed the Weka plugin, here in operators, beside the operators which come with RapidMiner, you're gonna have this folder extension with a few of the stations already come with RapidMiner, but with 131 additional operators coming from Weka. And one of these operators is the Weka base net. You can see that this operator is white. That's because it's not a native RapidMiner operator. And we typically have less options to configure properties of those operators than we will have for native RapidMiner operators. If we use it with the settings by default, we see here the Bayesian network which was trained is the topology where the class, the label, is connected with each of the attributes. This is really equivalent to naive Bayes, and we see here the performance which is similar to the one of naive Bayes because the expressive power of the model is really the same. If we change one of the properties of the network and instead using K2 topology, which is the one where the class is connected to each of the attributes, we use the tree augmented network topology, which is more sophisticated. When we run the model, we're going to see the tree. The tree in this case will be A1 connected to A3, connected to A4, connected to AT. This will be the tree part of the network. And the augmentation is connecting the label, the class, with all the different nodes. And in this case, the performance is still more or less the same because we already have a quite high performance, but typically this topology for the Bayesian network is a little bit more powerful. If you click on the nodes, you're gonna be able to see discrete probability tables which have been built. In the case of the Weka plugin, it will discretize the input and it will always create discrete probability tables for the Bayesian network instead using continuous probability tables by using, for example, Gaussians. Let's go back to the design. Another type of model we have covered are neural networks. For example, the standard neural networks. If we run this process, we're going to be able to see the topology of the neural network. These four light brown nodes are the four input parameters plus an offset, adding additional offset which is added. This will be the hidden layer, and here I have three output parameters, three output neurons. Each of these neurons is representing one of the three iris flower species, and each of these neurons should be activated only when the instance presented to the input, the attributes of the instance presented to the input corresponds with that species of iris flower. I can see if I put the mouse on top of the connections, on top of the neurons, I can see the weights connecting that neuron. For example, with the attribute A1, the weight is minus 0.31. With the attribute A2, the weight will be 1.8. With attribute A3 is minus 2.3, and with attribute A4 is minus 2.39. And the offset was minus 1.6. Those are the numeric values of the connections of this neuron with the input neurons, which in this case represent the features of the feature vector and the offset. I can configure the topology of the network. For example, I can add more hidden layers. By default, it will just create a single hidden layer, but let's suppose I have hidden layer number 1 where I want 8 neurons, hidden layer number 2 where I want 12 neurons, and hidden layer number 3 where I want 6 neurons. And now if I run this more complex neural network, it's going to take a little bit more training, and it will have the number of neurons in the first, second, and third layer that I have specified. The performance, well, the performance for this case, it actually has decreased because that's probably way too complex neuron for this problem, and it's worthless to use such a huge number of neurons. So it's really not a good idea to add so many neurons for this problem, because I have made a way more complex than necessary neuron for this problem. Another type of neural network based algorithm we have covered in the course is deep learning. Deep learning, we don't have any graphical representation of the net. Typically these nets are really complex. They have many layers in cascade. A lot of neurons. Representing them graphically will provide not too much useful information due to the complexity of the net. And here we can see the confusion matrix and the accuracy that we can see that this is probably the best model we have seen so far, 96 plus minus 3% accuracy. The auto multi-layer perceptron model within RapidMiner is also a neural network where it will try to tune automatically the number of hidden layers in the neural network and the number of neurons within each of those hidden layers. And last type of model that we could apply for this type of class, for a nominal class, it will be support vector machine type of model among the ones we have covered in the course. In this case, support vector machines, they can only work with binomial classes because they are creating a single hyperplane to separate two classes. I cannot apply it therefore to the iris dataset. I could apply it to the golf dataset. However, support vector machines can only work with numeric features. And in the golf dataset, I have some nominal features. So before applying the support vector machine, I'm going to have to numerize all the features, and that's not done automatically by the support vector machine operator. So I'm going to use the nominal to numerical operator, apply over all the attributes, and now I can apply it and I get a performance of, well, 40% plus minus 43%, but we already know that this is a toy dataset and there are too few instances to really learn anything useful. So far we've been working with the models which are capable of predicting a nominal class, something which is a label. We're going to work now with a dataset in which the class is metric. The polynomial dataset among the datasets present in RapidMiner. In the polynomial dataset, I'm going to run the process despite it will produce an error, because I just want to have this operator with a check, which means I can inspect the data so you can see what type of data we are working with, because this is the first time in the videos that we are using this dataset. In this dataset, the class, the label, which is also called label in the dataset, is shown in green as always, and is a number. It's the first time we have something as a number, with a number as a class. Up to now the class was always a label. So in this case the prediction, it is a number, and the 5 attributes we have here, they are also numbers. If we plot them, you're going to see that this quite complex dataset where we can see no patterns, no cluster, no correlation among the different variables. And my goal will be to try to predict the numeric value, the numeric value called a label from the other 5 numeric labels. When Computing, when calculating a metric label, it has no sense to compute accuracy, because my goal is to try to get a numeric prediction as close as possible to the real value, not exactly equal to the real value. If the price of a stock tomorrow in the stock market is $105 and my model predicted the price will be $104.95, my prediction is damn good, really, really good, despite I didn't get it exactly right. So counting how many times I got it exactly right is not the best metric. Here the best metric is counting each of the prediction, how close is numerically in the Euclidean sense to my real value. Therefore, I'm going to change here the operator I'm using to measure accuracy. And instead using the operator called performance classification, which is measuring accuracy, I'm going to use performance regression, which is measuring the square error, which is a typical way of measuring the accuracy of predictions of a model capable of predicting something which is numeric. I'm going to remove the support vector machine and let's use, for example, a linear regression. We are using also a tenfold validation, applying over the polynomial dataset. Okay, I need to connect this to the first performance output port. If not, RapidMiner is not going to be happy. Here I can see the model. My model is multiplying the attribute A1 by 31.7 plus A2 multiplied by 49.4 plus A3 multiplied by 23 plus A4 multiplied by 3.7 plus A5 multiplied by minus 4.1 minus 300. That's the linear model I have built. And the error in this case is 82 plus minus 13. Regression is one of the types of models we have covered in the course which is capable of predicting a metric label. Another of the models we know which is capable of predicting a metric label is the neural networks. So let's use a neural network. And let's see how good the prediction is in this case. The error went down significantly. Now the error is 35 instead 80. If we probably use deep learning, which is also capable of learning metric. Oops, I don't know what I have done. If we use deep learning, we may even get better results. Well, in this case we didn't really get better results. I guess the model is too complex for this type of data set, or we should have to tune some parameters. Sometimes it is the case that by using more complex model, despite the model theoretically has more expressive power than the more simpler models, you don't get better performance because you have more parameters to estimate with the model, and especially if you don't have a very large number of training data, estimating more parameters is harder. So in this case, the simpler neural network is performing better than the more complex deep learning algorithm. We have not covered all the models in RapidMiner. You have 61 different predictive models within RapidMiners, plus another 50 or 60 if you have installed the Weka plugin. There are different variations of the models we have covered in the course. There are different variations on what exactly is the metric used, for example, in the decision tree in order to compute the purity of the leaves. There are Bayesian approaches which are not based in parametric methods, where we have a standard, where we have Gaussians in order to represent metric data. but they are using non-parametric type distributions and so forth. In general, there are a huge number of different techniques available in tools such as RapidMiner. It is good to have a general idea about how exactly they work, and if you want to know the details because you think a given technique may be the best one for your problem and you want to learn how to fine-tune the different parameters, checking the help of the tool, learning a little bit about that tool is the best option possible. My goal with this course is to give you an overall overview of the different options available, instead focusing most of the tool in a limited number of set of techniques that we cover in great detail. That's everything with this video. We still need to know how to evaluate more properly the models than just computing accuracy or the square error in the case of a metric label. We'll see in other videos that evaluating models have a little bit more complexity that it may be obvious at this point, even with what already have learned regarding model evaluation in this video. See you in the next video.